Good morning, everybody. Thank you for the music, but now it's time to mute the microphone. And it's time for us to work. Okay, thank you. And so, first of all, before we start, although, of course, those who come later will again have questions about all this. So I guess I will have to repeat that, but not today, in the end of the lecture. I'm starting the lecture with some announcements. So the first thing is, those of you who live or who are staying here in Riga know that next weekend, that is this coming weekend, from Saturday to Sunday, we are changing our clocks, spring forward. That is, we are turning our clocks 1 hour ahead, forward. So those of you who are at home and in countries where you do not have summertime, where you do not turn the clocks forward in spring and backwards in the autumn, please note that starting from next week, we will be time zone GMT +3, not GMT +2. So that means that the lectures for you will start 1 hour earlier. Those who are turning the clocks forward for summertime, no worries, the timing will be the same. But if you are in a country where you do not turn the clocks, then please note that starting from next week, the time zone changes. GMT +3 starting from next week. That's one thing. The next announcement is that in the first weekend of April, we have Easter, and traditionally the Friday before the Easter and Monday after Easter Sunday are free. They are bank holidays. All state offices are closed. So there will be no lectures on those 2 days. The 2nd of April, which is a Friday, and the 5th of April, which is a Monday. I have put that announcement in Ortus already. And finally, some people already have asked me when we are going to have the test about the conic sections and analytic geometry, Unit 3. We still have material and serious material to cover in analytic geometry, which means the test will be, well, not next week, but I do believe on Wednesday after the Easter, that is on the 7th of April. Well, that's my estimate. The 7th of April, which is Wednesday, which means next Wednesday I will give you the homework. Maybe Tuesday, depends on how fast I can prepare it and upload it. And the 3rd unit test, not next Wednesday, because we still have a lot of material to cover and 3 lectures will not be enough for that. But seeing that we are actually going to miss out on 2 days, which is not a big problem, we'll still finish on time. Everything is computed and calculated. Time-wise, the schedule is settled. So the unit test number 3 on approximately the 7th of April. That's an estimate. After that, about 1 week later, we will have the first midterm examination. The first midterm examination, that is about the first 3 units. However, in order to be admitted to the first midterm examination, those of you who are required to attend elementary mathematics must attend elementary mathematics, and everybody must have written the first 3 unit tests. Not necessarily pass them all. That would be, I understand that in some situations that might be a bit difficult if you are struggling somewhat, but you must have at least attempted, seriously attempted. So sending me an empty paper doesn't count, but at least attempted and done your best, whatever you can do at that moment, for the 3 unit tests. That is the material pertaining to the first half of term. So you have, evidently, until then, that would be until mid-April, evidently, mid-April will be the first midterm examination. Until then, you need to settle your debts with the first 3 unit tests. I don't mean the debts where you were attempting and failing, but necessarily, if you have not even attempted a unit test, then that means you won't be able to write the midterm examination, which again causes problems, which again will cause problems, because writing the one and only final examination in June, which will determine your whole mark for the semester, will be much more difficult. So I seriously advise you to think ahead, study, work in class, and if you do that, then everything should be okay. All right, now to mathematics. To mathematics, the conic sections, second order curves. We started by looking at the circle, by looking at the ellipse, and remember that there were 2 kinds of ellipse. Basically, the horizontally placed ellipse with the foci on the x-axis, and the vertically placed ellipse with the foci on the y-axis. Canonical equations pertain to the ellipse, which is, in fact, situated so that the center of the ellipse coincides with the center of the system of coordinates, and the foci are on one or the other of the axes. If the ellipse is somewhat skewed, slanted, then the equation becomes much more complicated. We will not go into those situations in this course. And so today we have to deal with a hyperbola, although I'm not exactly sure. I think at which moment I wanted to talk about the different, like after the parabola. I remember now where I had planned to talk about the conic sections. I remember that I promised you an applet, an animation where you can see how these different sections are caused, but that will be today, but just a little bit later. So the hyperbola, we already noted last time that the hyperbola is the locus of all those points. Just a moment. Of all those points. One moment. I need the color of the light. Okay. So the locus of all points in the plane for which the difference of the distances to 2 given points is constant. That is this situation. Now I will attempt, just a moment, I will attempt to show you how that happens, just like I did with the ellipse. And that is this. And that would be this. I hope you can see this. Yes, you can. And so the hyperbola actually is the locus of all points where the difference of the distances from the point on the ellipse, that is the point M, to the 2 points F1 and F2, which are called, of course, the foci of the hyperbola, are actually, the difference of these 2 distances is constant. The difference of these 2 distances is constant. You see how both distances become greater, they become longer. However, the difference between these 2 is constant. And we can see that if I say that the difference of these distances is 2a always, then if you note that this distance from point M, where it currently resides, to the point F2, for example, 2 units. The distance from the focus to the vertex of the hyperbola is the same, of course, as the distance from the other focus, F1, to the vertex of the hyperbola, to the point -3 on the x-axis. So in principle, the difference of these two distances between M and F1 and M and F2 is 2a, which means that this point, the vertex of the hyperbola, as we call it, and the other point, they have coordinates a0 and -a0. In this picture, in this particular hyperbola, we have a situation where just a moment, yes, where the a value is 3, and the c value, the coordinate of the focus, is 5. But of course, depending on these numbers, the hyperbola could be wider or narrower. It depends on the constant. Now I am returning to the old share. So now I am going to go back to my old share, and now let's go on. So the foci F1 and F2, just like the ellipse has 2 foci, the hyperbola also has 2 foci. And the equation, then, canonical equation, in this particular situation is x squared over a squared minus y squared over b squared equals 1. So the difference from the equation of the ellipse is this sign. The difference is this sign, minus sign. So that sort of, as you see, it looks like it turns the ellipse inside out. It looks like as it turns the ellipse inside out. Imagine that the points where the ellipse meets the y-axis, the points B and minus B on the y-axis, they are flipped outside and projected to the infinitely far points in the plane. So it's as if the ellipse is simply turned inside out to both sides. That might be an analogy, perhaps a bit easier to understand where this all comes from. Well, that's one way of viewing the hyperbola. It's not very helpful for actual calculations and actual use, but at least some idea of how we might compare these two curves. So A is called the semi-real axis, as I already noted last time, or transverse half axis. Transverse meant intersecting. Transverse means going across the hyperbola, intersecting the hyperbola. And B, the value B is the semi-imaginary axis. The whole value 2b, the distance between these 2 points, is 2b. It's called the imaginary axis or conjugate axis. And if we have the half value, the b value only, then we have half of that semi-imaginary axis. Imaginary because it's not something real, because in reality, directly, it has no relevance to the hyperbola, at least no obviously visible relevance to the hyperbola. They are not points on the hyperbola, unlike the ellipse. That's why we call it imaginary. Conjugate means conjugate axis or conjugate half axis means it is linked to the transverse axis. Conjugate means something that is linked together with something else. So in this case, the transverse half axis is the one that actually intersects, goes across the hyperbola, and the conjugate axis is the one that is connected to it. In this case, it's perpendicular. I'm sorry, one moment. Back. And now. And now, so the foci C0 and minus C0. So in reality, in fact, for example, we see the foci, so this is minus C, this is the second focus with coordinate C, so this is A. So it's not very visible. I copied this from a book, and that's why it's not very obvious to what the A pertains. A pertains to the vertex. A pertains to the vertex. And then there's some value B, who knows what it means, but we actually have a very good understanding of what it is. So first of all, the C value is, according to the Pythagorean relationship, a squared plus b squared equals c squared, which actually means that, for example, this segment, this half diagonal of the rectangle, evidently that has length c. This has length c. So if we have a rectangle passing through the points A on x-axis and B on y-axis, so the sides are 2A and 2B, then evidently half sides in this small rectangle, we will have A and B, and this would be C according to the Pythagorean theorem, according to Pythagoras, here at this point, which actually means that if you have marked in the plane, if you have marked the hyperbola, including this rectangle, you can actually imagine an arc if you have compasses, and you can actually draw this arc, or at least measure this distance to find the focus on the axis, on the x-axis. That's a possibility. It's not strictly necessary, because we will not be able to evidently to plot these hyperbolas very, very accurately. That would take finding many points, or a graphing software, which is, in that case, we don't need to find the focus. All that it takes is compute it and mark it there. So, but if we are required to graph something by hand, then you should understand that this half diagonal of the large rectangle actually equals the focal distance from the center. That's an interesting thing with the ellipse. This is not true for the, with the hyperbola. This is not true for the ellipse. It's only for hyperbola. Eccentricity, again, something that I already mentioned at the end of the last lecture. Eccentricity, just like with the ellipse, is C divided by the, in this case, horizontal half-axis, the focal distance from the center, divided by the half-axis. As you see, C is greater than A, which means eccentricity of a hyperbola is actually greater than 1. And the greater this eccentricity is, the further away the C value is. The foci are further away from the center, which means the ellipse is evidently thinner and longer. The closer to 1, the flatter that ellipse, the hyperbola, this is hyperbola, I'm talking about hyperbola. The closer to 1, let's say the flatter this ellipse is, and in fact, if it's 1, it could even become, let's say, a pair of 2 lines. However, that's not the case. That's not what we consider, because in that case, it will not be a second order curve. That will be something completely degenerate. Now, asymptotes. This is why we need the value of B. This is where the imaginary half-axis comes in. The asymptotes are these dashed lines which are approached by the hyperbola, and already we had a question last time. Do they ever intersect the asymptotes? No. The asymptote, translated from Greek, means something that is not falling together, which means the hyperbola will approach the asymptote infinitely close but it will never intersect the asymptote. It will never become actually the asymptote. It's like approaching closer and closer and closer, very, very gradually, infinitely close. That means if we go far enough, we can get as close as we wish to the 1 millionth of a millimeter or 1 billionth or whatever. All it takes is go far enough along that asymptote and you will reach that point where the distance between the hyperbola and the asymptote is that very, very tiny one, however, never actually zero. And the equations of the asymptotes, as you see, asymptotes are lines. The equation of the asymptotes is this: plus b over a times x minus b over a times x. Rise over run, if you remember, rise is b. Notice, rise is b, run is a. So that's why we have rise over run, and that would be b over a. And the other one, of course, the rise is negative b because it's going down there, so that would be minus b over a. The two lines, two asymptotes, have these equations. Plus minus b over a is the coefficient times x. So again, if I wanted to show you how we acquire this equation in this canonical form, it would take a lot of algebra. It would take serious algebraic transformations, and we simply don't have the time or the need for that. So if you want to see those transformations, of course you can easily Google them up and find them online in any site that describes the second order types. Now we have this other thing. The hyperbola, yes, we could use the same plane, but this hyperbola opens up and down, opens vertically. Not horizontally as the previous one, but vertically. Note that it is using the same numbers b and a, the same asymptotes, as you can see. The only difference is that the hyperbola is inscribed in the upper and lower angle, not in the side angles, but in the angles placed vertical, in the vertical angles. So it's called a conjugate hyperbola. Conjugate, that is connected, conjugate to the previous one, conjugate to the old hyperbola. The actual difference is that we could say it's y squared over b squared minus x squared minus a squared equals 1, or the same difference, but instead of 1, we have minus 1 here. So as I said, we can rewrite this equation as y squared over b squared minus x squared over a squared equals 1. So these like swapping places. It's the same thing. It means the same thing, but we generally use this minus 1 because it's easier to perhaps remember. But it depends on how you do this. I have no objection. If you prefer this equation. Just remember that y is always connected to b. So b is always on the y-axis, and minus b is always on the y-axis. And x is always connected to a, that is the points a and minus a are always marked on the x-axis, always. It doesn't matter whether just like with the ellipse, it doesn't matter whether the ellipse was horizontal or vertical. It doesn't matter whether the hyperbola is horizontal or vertical. A is always pertaining to x, and b is always pertaining to y. Those are always the points on the x-axis and y-axis correspondingly. Never try to change them. That would be an error. It's a convention, and that's easier to remember. In case we ever have doubts, for all curves, we mark the intersections or the critical points on the x-axis by A, and the interesting points on the y-axis by b. Remember that even with the straight line, we had the same a for x and b for y. So that will be, let's say, as a rule, And so the conjugate hyperbola, I will now erase these extra scribblings and I will move on. So again, now A is the semi-imaginary axis because the horizontal axis does not intersect the hyperbola. And B is the semi-real axis. Correct. B is the semi-real axis because the vertical axis is transverse. Vertical axis goes across this hyperbola. So the names change. The situation with the foci changes. Now the foci are actually on the y-axis. C and minus C. So focus at 1, C minus, C0. So C0 and F2 minus C0. Sorry, it's the other way around. Of course, I had to. I was still thinking about the previous parabola, the hyperbola. I apologize. I am evidently slightly absent-minded today. So F1 with coordinates 0, C, and F2 with coordinates 0, minus C, as I wrote it here. That was the correct version. And again, yes, we could still have the same connection between a square and b square. It's still c square. So the focal distance is exactly the same as for the first hyperbola. The shape is different because now we are actually doing different things because the real axis is now 2b instead of 2a, but the focal distance is the same. See, we still have the same c value. So if I draw the other hyperbola here, like this, you see the shape would be different. This hyperbola would be narrower, thinner, more stretched out. And this vertical hyperbola, this conjugate hyperbola, is flatter. Of course, that depends on A and B values. If B is greater than A, then it will be the other way around. The vertical hyperbola would be thinner, and the horizontal hyperbola would be flatter. So the essential properties of ellipse and hyperbola are different. They are different. The thinness or the flatness does not exactly depend on which is greater, A or B, but also on whether we have the regular hyperbola or the conjugate hyperbola, which opens upwards. In other words, it depends not only whether A or B is greater, but also whether the foci are on the x-axis or y-axis. In the ellipse, these things were connected. If A is greater, then the foci were on the x-axis. If B was greater, then the foci were on the y-axis. In hyperbola, the situations actually could be all kinds. So for the ellipse, only 2 possibilities. For the hyperbola, evidently, 4 possibilities, A greater or B greater, combined with the foci on the x-axis or the y-axis, which was not true for the ellipse. So there's a difference. Eccentricity, C over B, just like with the vertical ellipse. Evidently, the vertical hyperbola and vertical ellipse do have something in common. They do have something in common, and that would be C over B. I also note that we have 47 people online, but not everybody has written attendance in the chat. So I am assuming that those people just either switched on the computer and left, or are completely forgetful and absent-minded. So that looks like it's the first case, because evidently they are not listening, because otherwise they would write their names in the chat now. Okay. Okay. And so the eccentricity always goes as the focal distance from center versus semi-real axis. Always, always, always. And that's more or less it at the moment, theoretically. Theoretically. So the asymptotes are the same as we see. The A and B values are the same. The focal distances are the same. The only thing that changes is that hyperbola is not the horizontal hyperbola, but the vertical replaced line. And all that depends only on this one sign, +1 or -1. Or do we subtract x squared minus y squared, or y squared minus x? So what you will be required to distinguish is, if you have an equation for a second order curve, you must be able to determine which kind of curve it is. Is it an ellipse? Is it a hyperbola? Perhaps it's a circle, perhaps it's a parabola. So recognizing those equations is important, of course. Now let's move on, and we will have some exercises. And so, in the first case, we will assume that the hyperbola is symmetrical about the origin on the x-axis. So that will be the horizontal hyperbola. Let's just see what happens there. We know that for the horizontal hyperbola, the general equation is x squared over a squared minus y squared over b squared equals 1, because we have the foci on the x-axis. So we need to write the canonical equation, which means what we need is a, or a squared, and b, or rather b squared. How do we find those? First of all, if the asymptotes are these, remember that an asymptote is y equals plus or minus b over a x. So this means that I could, for example, take this and see 3y equals to x. So y equals 2/3 x, which means b divided by a is 2/3. What this means is not that b is 2 or a is 3. No, not necessarily. It simply means that the ratio of b to a equals 2 to 3. That's the only thing that we really know. So in principle, if I want to find b, I could say b is 2/3 of a. b is 2/3 of a. And so now what we have to do is, first of all, we have a point, and that means, remember from the previous cases, that means we can put this point instead of xy into the equation and simplify. So perhaps we don't need to put b equals 2/3 of a in there immediately. Perhaps we should start by simplifying this equation, first of all, having a look at what happens when I put the coordinates of this point n into this equation. That's something we can do for sure, and then if we need to do something else, we can always do it. So x squared will be 36 over a squared minus y squared now, negative 2 square roots of 2 squared is 4 times 2 is 8 over a squared equals 1. So now b squared, I'm very sorry, b squared. And now we have a look at this b equals 2/3 of a, and it looks like we need to put it inside. So sometimes the equation can be simplified algebraically enough so that we might work with it somewhat differently. In this case, it does look as if we need to substitute b is 2/3 of a. b is 2/3 of a. And so let's see. We have 36 over a squared minus 8 over squaring 4 over 9 a squared equals 1. Then remember how we divide by a fraction. We change things. We multiply by the reciprocal. In other words, if I divide by 4/9, I have to multiply by 9 over 4. So first of all, I change this 36 over a squared minus 8 over 4a squared, but 9 goes up equals 1. And then I can, in fact, for example, multiply everything by 4a squared. Or actually, no, I can first of all simplify. It's always best to simplify as much as we can. So we have now 36 over a squared minus 18 over a squared equals 1, which means I have 18 over a squared equals 1, subtracting the two fractions, which means a squared is 18. And then, because I know that b squared is 4 over 9a squared, it means 4 over 9 times 18, and that means it's 8. 18 and 9 simplified. 18 and 9 simplified. So this means now that my final equation, I can now write the final equation. Color, yes. The final equation would be x squared divided by a squared, which is 18, minus y squared divided by b squared, which is 8, equals 1. So this is the canonical equation of the hyperbola that has these asymptotes and the point through which we know it passes. So it takes, as you see, a lot of analytical work. That's why it is analytic geometry. The hyperbola could be, well, we started with a hyperbola, describing it geometrically as the locus of all those points that have a certain geometrical property, but we end up doing a lot of calculations, doing a lot of algebra. So to sort out things, we started with this. We then put in, then this was the next part where we actually inserted the coordinates of the point. Then this was the third part where we actually expressed b, or we could start with that. We could take this as the first part, it doesn't matter. And then this is the fourth part where we actually put also the b and a connection into the equation. And then after that, we simply find and evaluate the value. So the location on my board is slightly messy, if you like, but I have tried to at least number things properly so that you see how it works out. So we start with the general canonic equation without knowing anything. Then we put in the known coordinates of a known point into that equation. Then we also put the expression b, the connection b and a into this. We have two unknown constants a and b. That's a bit too much. But fortunately, from the asymptotes, we could find the connection between b and a. And thus we could express both constants a and b through just a. And then the rest is algebra and simplifying. The rest is algebra and simplifying. 5, 6, 4, 5, 6 is basically algebra and simplifying. So we start by putting into the equation whatever we can, known points, known connections, and then do things analytically or algebraically. All right, I'm moving on to the next example. So this was not a simple one. This was not a simple one because in general I could actually state something very similar to the situation with the ellipse. For example, write the equation for the hyperbola that has transverse axis this and the focus there, and just write down ABC. That can of course always be done, and for the sake of revision we will next time probably have a look at a couple of examples like that. All right, here we have, and I lost x, I'm sorry, so we have x there, and the asymptotes are plus minus 12/5 x. So the distance between the vertices is 48. The vertices and the symmetry is on the on the y-axis. So this means this will be the conjugate hyperbola because the foci are on the y-axis. So first of all, the first thing I need to note is, of course, I need to write the general canonical equation x squared over a squared minus y squared over b squared equals minus 1. I have to remember that it will be this one because of the y-axis. That's the first thing. The distance between the vertices. So now we remember that evidently it will look like this in general, and the distance between the vertices is 2b in this case, because remember the distance is on the y-axis. The distance is on the y-axis, and therefore it is 2b because the hyperbola is vertical. 2b equals 48. That means b is 24. And the asymptotes are these, which means from this on the other hand. So this is where we started. Then we know this information. We have b. Number 3, the third step. The third thing that we do is evidently b over a is 12 over 5. But we know that b is 24. So we could say it is 24 to a. B is 24. B is not 12. A is not 5. It's only the ratio simplified, because who wants to have an equation for an asymptote or for any line without simplifying? Of course we want to simplify it, and therefore we have to remember that the numbers that you see in the asymptote, the numbers that you see in the eccentricity, they are basically almost never the actual values of A or B or C. They are only ratios. They are only ratios. So from this, then we can conclude that evidently A is 10. From this, we can conclude that A is 10. So never take this ratio for granted as the finished numbers. It's only the ratio. So now we have B, we have A. So this is very typical. X squared over 10 squared, which is 100, minus y squared over 24 squared, which is 576, equals minus 1. And there we have it. It's done. So in this case, this situation was simple. See, because all you had to do is find the constants, and one constant was already, the constant b was already practically given. The catch in this question, the catch in this task was understanding that it is b and not a, the distance between the vertices. The catch is understanding it is the vertical hyperbola. This is something that people sometimes miss by b. careless, for example. So similarly to the exercises with ellipse, you could have a situation, for example, where the focal distance is given, or where the eccentricity, for example, could be given. So again, we do the things very, very properly like this. So in other words, if you have two constants, then just like with the ellipse, from those two constants, like for example this and this, from those two numbers, you basically can get everything else that is necessary for the equation. Algebraically, using pure algebra, using the connections between the constants. See, we didn't use the equation itself till the very end. Here in this part, we didn't need the equation of the hyperbola. We needed the, let's say, the known connections between the constants. And I will remind you, the known connections with the constants was the equation for the asymptotes, the eccentricity, which was C divided by A or B, depends on which one, so the real semi-axis or semi-real axis. And then we have A, and then we have B, and then we have C. So as you can see, we have 5 possible constants. If we know 2 of these, we can write the equation, surely. If we know A and B, we can write the equation directly. If we know one of those, A and B, and another of these numbers, whether it's the ratio B to A or the eccentricity, we can figure out the other number. So in principle, you need exactly 2 numbers. You need exactly 2 numbers for this. Okay, now let's go on. We have more exercises for this. All right, we have a hyperbola, and we need to find everything pertaining to this hyperbola. Actually, I would also like to find the eccentricity. We will also find the eccentricity for the hyperbola, and we will try to sketch it. For me, sketching in this mode, it will be a little bit more complicated, but still we can do this. So first of all, we can move 144 to the right-hand side, because we know we cannot have a 0 there. We need 1, or at least to begin with, some number that is not 0. Now the next thing is, we can now divide both sides by 144 to get 1 on the right hand side. So 9x squared over 144 minus 4 y squared over 144. And that would be x squared divided by, looks like, it is 4, so it's 164, no, 144, and there's 9, 154, 16, sorry, and y squared divided by 36 equals 1. So basically we see that A is 4, and B is 6. That's something we can already mark. So if this is 4, and then this is 2, 4, this will be 6. So 2, 4, 2, 4, this will be minus 6, and this will be minus 4. This rectangle, we can already start by sketching this rectangle lightly. That was the famous 2a by 2b rectangle. We can start by sketching that one, because from that it doesn't matter where we have the cosine at the moment. Yeah, so it's this. So this is the y-axis and this is the x-axis, right? So we have this. First of all, we have plus 1 here. This is plus 1. This means this is the direct hyperbola. This will be the hyperbola opening sideways, not up and down, but sideways. from +1, we can conclude that. Now, the foci, evidently c squared is a squared plus b squared, that is 16 plus 36, and that is 52. So c would be the square root of 52. So c would be square root of 52, or we could say, because 52 is 4 times 13, we can say it's 2 square roots of 13. It would be rather messy here to compute and evaluate approximately, and this is why I will actually use this trick with the arc. I will just change the color because it's definitely something that's an additional thing. So actually, if this is A and this is B, remember that this distance then is C, and I imagine that I have compasses, and I can actually mark that point C. So this will be the focus F1 with coordinates evidently 2 square roots of 13, 0. And similarly symmetrical on the other side, we will have -2 square roots of 13, 0. That will be somewhere here, and I'm doing now it's just by the eye. This will be F2. We write down the coordinates. You might not write down the coordinates in the sketch. As long as you write them down in the solution and mark the points F1 and F2, that would be sufficient. So at the moment, we can already sketch it. All that we need to do is write down the asymptotes and the eccentricity. So we can almost already sketch it. So the asymptotes will be y equals plus or minus. Remember, b divided by a. B over a, that is 6 over 4x, or we can say y is plus or minus 3/2 x. That would be the equation, the two equations for the asymptotes. We can sketch these asymptotes like, okay, let's draw the lines. There is the one asymptote. I should actually sketch it completely. This, there, the asymptote, there we go. And finally, just sketch the asymptote. Oh, and write the eccentricity, of course. So the eccentricity, as we know, is c divided by a, because it's the horizontal hyperbola. C is 2 square roots of 13. A is 4, so we have root 13 divided by 2. Square root of 13 divided by 2. That's the eccentricity. Not something very nice, not a nice number, but if necessary, we can actually sketch it. And now all that remains is actually sketching that hyperbola. So this is the vertex. The hyperbola will pass through this point, through the vertex, and it will approach the asymptote, but approach the asymptote closer, but never actually intersect it. So all we can do at the moment is sketch it approximately. If we want to make it more accurate, we need to find more coordinates for more points. I am not asking that in any test or examination, but what I am asking you to do is to make sure that you get all the points correct, that you have marked this magical rectangle for the hyperbola, you have marked the asymptotes, and you have, in fact, sketched the hyperbola and seen the vertex correctly, seeing the foci, and seeing actually the coordinates of the foci written, and the values of A and B written, and evidently the coordinates of these points also visible, the real half-axis, the imaginary half-axis. So this would be a complete investigation of the hyperbola. A complete investigation of the hyperbola. You realize, you understand all the constants, you have found all the constants, you have written the equation in the canonical form, because from that you can already sketch it, in fact, without marking, perhaps without marking the foci, but as soon as you have the canonical equation, you can sketch that rectangle, you can sketch the asymptotes, even if you don't know their equations, and you can sketch the hyperbola, even if you don't know the foci, but then remember that you can also mark each focus. You can mark focus. So, yes, I understand that sketching the hyperbola is a little bit messy, especially if you don't have graph paper, if it's all by hand. So you need to practice, you need to train your hands to obey you, to do some sketching that is, let's say, perhaps not exactly very precise, but at least accurate enough to give the correct impression. Please understand that I will not count any pictures where the hyperbola goes away from the asymptote, because I have seen people who sketch something like this. Well, now this is it. No, this is not it. The shape is completely wrong. So please make sure you sketch accurately, precisely, and very, very carefully. I'm not asking you to do lots of sketching in this course, but sketching the hyperbola accurately, sketching the ellipse accurately, or at least as accurately as you can, is something you need to do. Okay. Now, let's see what else is there. Another hyperbola, very similar to the previous one. We still have 144, somewhat different numbers compared to the previous one. Now let's see what happens here. Can you see the difference, the main difference? The main difference will be that the number on the right-hand side is negative. This means it will be the conjugate hyperbola. Now again, we still can divide both sides by 144, and that will be x squared divided by 9 minus y squared divided by 16 equals minus 1, because 9 times 16 is 144. So this will be the conjugate hyperbola. The foci will be on the y-axis. We can already again sketch the frame. 1, 3. So we see that a square is 9, which means a is 3. We see that b square is 16. That means b is 4. From there, we can actually find c square is a square plus b square is 25. So c is 5. So the basic constants are all there. We can do 3, 4, 3, 1, 2, 3, 1, 2, 3, 4, and we need 5 for the focus. And 1, 2, 3, 4, 5 is the next, or we need minus 5 for the focus. And that. Now we will connect that rectangle through this box to 4, only count the squares. So this is where the square paper is actually very useful. We can already actually sketch in the basically, it's just enough that you mark some numbers on the axis in the picture, and you already have a lot of information to go for sketching the hyperbola, x-axis and y-axis. So we have focus F1, we have focus F2. We can write them down. F1 has coordinates 0, 5, and F2 has coordinates 0, minus 5. We can also write down the eccentricity. Eccentricity is c over b. Remember that b is the real axis now. not A, but B in this case, so it will be 5/4. The eccentricity is known. Now the asymptotes, of course, the asymptotes are plus minus B/A times X. That means plus minus 4/3X. So we have the foci, we have the asymptotes, we have the eccentricity if necessary, and we have everything we need to make a sketch. So it doesn't take much time if you know what you are doing. So I sincerely hope that you know what you are doing in this situation. So this is the focus, but this is the vertex. This is the focus, but this is the point. This is the point on the hyperbola. This is the focus, this is the vertex. This is where the hyperbola actually intersects the y-axis. That's why it is the real axis, the real distance between the two extreme points of the hyperbola. And now all that remains is, let's say, keep your hands steady, and try to draw that hyperbola. This. Okay, my hyperbola is a little bit shaky. I am absolutely sure that with a pencil and paper you are able to draw it more accurately. If you are not in a hurry, if you don't do just slashes on the paper, if you do it more or less accurately, this is what you get. And well, hopefully more accurate, more precise than mine. Seriously. Okay. So this is how we, let's say, get the hyperbola made. This is how we actually obtain a hyperbola. Now one more, slightly more complicated situation about the hyperbola. So verify that the point A lies on this hyperbola. All right, we can, first of all, we can in fact put the values of x and y into the equation. So that would be 5 squared, 25/16 minus 9/4 squared, that would be 81/16 divided by 9 equals 1. I could multiply everything, both sides of this equation, multiply by 9. So I have 25 times 9/16 minus 81/16, simply because when I multiply by 9, you know what happens, what should happen. When I multiply by 9, this gets multiplied by 9, this gets multiplied by 9, so 9 and 9 will disappear in there. So we have this, and on the right-hand side, 9. And this is what we need to check. Is this true? So 25 times 9 is actually 225 minus 81 divided by 16 is in fact 144. And yes, it is indeed equal to 9. So we have verified that the coordinates of the point A work. So I'm inserting the coordinates of point A, xy, into the equation. I check that this equality actually is true, that I get that the point actually does lie on the hyperbola. Now I understand that this hyperbola is the horizontal one, opening horizontally, the standard hyperbola. And to find the distances, focal distances of a point, this means I want to know AF1, this distance, and AF2, the other distance. So how do I find these? I need to find the foci. I need to find the C value. I need to know where the points F1 and F2 are. So from there I see A squared is evidently 16, B squared is 9, which means C squared is 16 plus 9, as previously 25. So C is 5. Aha, now that's interesting. So if I sketch this hyperbola, and in this case, I really did it very, very approximately. In this case, I don't need a very accurate situation, but we see that this will be minus 4, this point will be 4, and this will be minus 5, and this will be 5. It doesn't have to be accurate. It doesn't have to be to the scale. I'm only sketching it so that we understand the situation. And now the thing is, minus 5, 9 over 4. 9 over 4, the y-coordinate is positive. So we see that the point A actually lies directly above the left focus. That's something that we need to notice. So this is where the sketching and the understanding of the situation comes in. We have to pay attention to little details. For example, here, yes, we do need the coordinates of the foci. We find the coordinate, we find the value C, and then we see that, oh, it looks like A minus 5, 9 over 4 is directly vertically above one of the foci, which means the distance from A to the focus, let's say F1, can be found very easily. I hope you see how. The y-coordinate of this point is 9 over 4, or 2 and 1/4, which means the distance from A to F1 can be, in fact, read, not computed, can be read off the picture, the diagram. It's not exact, it's not accurate, it's not to the scale, as you can surely see. It's definitely not to the scale, but it doesn't matter. We have 1 and 1/4 is the distance to the first focus. Now, if we look at the distance from the point A to the second focus, so F2 having coordinates 5, 0, we have options. So one possible option would be something that many people think of, the right triangle. We see that the shorter leg of this triangle is 9 over 4. The longer leg, the distance between the two foci is 10. So from Pythagorean theorem, we can find this other distance. So one possibility would be indeed use Pythagorean theorem. But there's another one which is better. Remember that the difference of the two focal distances is constant and equal to 2a. Remember the situation where we had a, f, in this case the f2 will be greater, this is the greater distance, minus a, f1 is equal to 2a, it's constant. And a is evidently, well, as we know, a is 4, that's already marked there. So a is already 4 and 2a is 8. So this means that AF2, the second distance, is 2 1/2, 2 1/4, so plus 8. Add the difference and you will get the greater distance, 10 and 1/4 units. And that's it. You would get, of course, you would get exactly the same, units, whatever they are, centimeters, millimeters, inches, whatever units. So you could have used the Pythagorean theorem. If you do arithmetics correctly, you will get exactly the same answer. But remember that the hyperbola is a special curve, and we started with a very simple geometric property. Well, maybe not so simple when you translate it to algebra, but from the geometrical viewpoint, it's easy to describe, and so we can use this difference between the two focal distances from that point. And so we find the second focal distance easily. So the distances are 2 1/4 and 10 1/4. What would have happened, let's say, what would be worse? A situation that might happen worse, and I simply do not have an example for that. I decided it was not really necessary. A situation that could have been worse would be if I had a point not directly above a focus. So I would need, first of all, to find the difference of the x coordinates. That is, I would need to find this side of the triangle. Then I would have to take, of course, the y coordinate of the point. I would need to use Pythagorean theorem to find this distance between 2 points B and F1. And then technically I would use this property. I would not use the Pythagorean theorem. That would be a bit too much, right? But so in case we have a point that is not exactly above the focus, in this case it was, and it was a good thing to notice it. But if it's not, then again we should sketch it. We should look at the right triangle, because remember, in the Cartesian system of coordinates, right triangle is the key to distance. Right triangle is the key to distance. So if you can see right triangles from which you can find the distance by finding the hypotenuse, then basically you win the situation. You can transform algebraically, you can do the arithmetics, and you can compute every distance that you need in Cartesian coordinates. All right. Now we are moving on to parabola. There's not so much time remaining for that. We have been discussing the hyperbola a lot, but that's understandable because hyperbola is actually the most complicated of all these curves. That's true, because we have more parameters involved. We have those asymptotes, and we have all these things. So now parabola. A parabola is defined again geometrically. It can have a variety of definitions, but we choose the definition of a parabola as the locus of all points in the plane equidistant from a given point and a given line. If you remember, in one of the first classes of, in the very first one actually, when we did the Cartesian coordinates, we had an exercise. Find the locus of all points equidistant from a given point and the y-axis. There was this task. We had the y-axis, we had the point, and we had to find all points equidistant from this point and the y-axis. And in fact, what we found was an equation for a parabola. So equidistant, same distance of these points to the point A and to the y-axis, which is perpendicular, like this, or anywhere else, to this point and to the axis, right? This distance. So that's how we define a parabola, as the locus of all points that are at the same distance from the given point, which we call the focus of the parabola, and from a certain line. So the points must be at the same distance from focus and this line. 1, 2, 3, 1, 2, 3. These distances should be the same. We call this point focus, and the line is called a directrix. Directrix because it directs the opening of the parabola. It directs the direction of the parabola. It kind of gives direction to the parabola, because the axis of the parabola, you know enough about parabola already to remember that it is again something very symmetrical. It's something very symmetrical. So actually this line is perpendicular to the axis of the parabola. The axis of the parabola goes through the focus and of course is perpendicular to the directrix. So the directrix is the one that's perpendicular to the axis. All right. The canonical equation of a parabola. We will assume we will place this parabola in the system of coordinates. The canonical equation of this parabola means that the focus is on the x-axis and the directrix is, as you can see, perpendicular to the x-axis. Oh, I don't have a picture for it. Okay, it's this. So the focus, okay, I will go back so that you have enough time to note things. Although, of course, everything is in the lecture transcript. The canonical equation is this: y squared equals to p times x. P is the distance between focus and directrix. And the equation contains double this distance. So which means that from the vertex to the focus, it's half of the distance, and from the vertex to the directrix, it's the other half of that distance. If we go now back to this, as you see, from focus, so the focus has coordinates p half 0. So this is p half. This is again the same distance, only the directrix has equation x equals minus p half. And this distance from the focus and the directrix is the parameter p, which is basically the parameter of the parabola. It determines the exact shape. The exact shape of the parabola is determined by one and only one, the single parameter p, which is the distance between the point, between the focus and the directrix. 1 point, 1 line, that's enough. The parabola is already determined. So, as you can see, there is no x squared. In the previous equations for circular, ellipse, hyperbola, we had x squared. For the parabola, there is no such thing as x squared. There's y squared in the equation, but no x squared. That's something interesting. One thing. Another thing, there are no two constants, two parameters like a and b, but like with ellipse and hyperbola, but there's one parameter only, and that is p. And the equation actually contains 2p. We write the equation 2px instead of something like mx, because we want to stress the distance between the line, between the directrix and the focus. That's why we have this equation 2px. We could have written mx, just combining this in a single constant. We do not do it because p is this all-important distance between the two very important objects. Now that's something that you should know. Okay, now this is the canonical equation of the parabola. For the canonical equation, for this situation, we say that the parabola opens up horizontally to the right. The focus is on the x-axis. Note that the focus is on the x-axis, and the directrix is perpendicular to the x-axis, and the vertex of the parabola is at the origin. So these are, let's say, a couple of interesting or important things. Vertex is at the origin, focus on the x-axis, directrix perpendicular to x-axis. And that's let's say the one of the canonical equations for parabolas, or we can say this is the canonical equation, but we could have some other possibilities. Now at this moment I would like again to demonstrate something. Let me see, you share this GeoGebra thing again, but right now I'm going to make the hyperbola disappear, and in fact I want I want this, 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 and I want this and this. Okay, so here we have the let's say the parabola with the classical equation y squared equals 2px. Here we see a point on the parabola. Here we see the point on the parabola that actually, okay, I will move it, which, as you can see, the distance from this point to the focus and the perpendicular distance to the directrix is the same all the time. As you can see, we can move this point, I can move this point, and of course here it's p half to one side, p half to the other side, and there we see again we have the same distance to the focus and to the directrix. The length of the perpendicular MB is the same as the distance from the point N to the focus F. This is how we have actually situated this parabola. The point F2 actually doesn't count. I left over from the hyperbola. I forgot to hide it. So this point, ignore this point, please. Now, let's see how this distance P influences the shape of that whole parabola. Now, I will leave the point M in peace, but I will change the parameter P. As P increases, see, now P is 2 at this point, focus is at 1, and the directrix is at -1. The focus is 1, 0. If P increases, see how the focus and the directrix move apart from each other, and the parabola becomes flatter, it becomes wider if P is greater than, if P becomes greater. Now, if P becomes very small, we see the parabola becomes thin. So in principle, the smaller the p-value, the thinner and longer the parabola is, as you can see. And then if it's 0, then the parabola disappears because focus, evidently focus, the distance from the focus to the directrix is 0, and all points have there's no parabola at all. But if I take p is negative, see what happens? We go to the other side. Only because p is the distance, p technically, formally, should not be negative. And this is why we will always say p is positive, but if we have an equation where the coefficient is negative, we will simply understand that the parabola goes facing in the negative x direction. And, yes.
So I have a question, right? So will there be a point where P makes the parabola into a straight line?
Not exactly. In principle, not exactly, because the distance to the p-value, so parabola should not become a straight line for the reason that the distance from any point of that line then should, let me get there. So it should be, see, if, for example, if I take, you might think, is it this line or is it this line? The distance, yes, it does become the straight line. It's not the y-axis, it's the x-axis. However, it's the x-axis. You are actually right, because if I take a point, let's take F2 for example, if I take a point here, the distance to the point P is basically the same as the distance to the y-axis, to the directrix. That's true. From any point here on the x-axis, the distance to P is the same as the distance to the y-axis. Yes, this degenerate parabola is actually the straight line. That's a very good observation. That's a very good observation. Thank you. That's interesting. But yes, you are right. Okay, I'm going to go back to this because I will need this at some point, maybe later. And now I'm going back to share these everywhere. Back to this. So now we see that sometimes, so yes, the directrix, sometimes the parabola goes facing in the other direction. So if the parabola opens to the left, as we saw, if the parabola opens to the left as we saw, then evidently we have an equation with a negative coefficient. In my demonstration, it actually appeared as if P is negative, but P is that distance, so P should not be negative. We will simply understand that P is still positive, but this minus means that it opens to the left, because X values then must be negative. See, Y squared is always positive. So if I have a minus here, a negative coefficient, then X only works if it's negative, because negative times negative is positive. So that's why it opens to the left. And of course, the focus is at the point now minus P half, and the directrix is at the X equals pi half. Now, what happens? Can we have parabolas opening up or down, like in normal calculus, like in school mathematics with functions, like quadratic functions? Can this be true? Yes, of course, we can actually depict the exact same situation, only the focus will be on the y-axis, and the directrix will be horizontal, not vertical, or focus will be on the negative y-axis, and the directrix will be horizontal. So we could have a situation x squared equals 2py. All we have to do is exchange x and y, and it opens up. And the focus is on the y-axis, and if we want a parabola to open down, then we have x squared equals minus py, and the focus is down there. And remember that the directrix, I didn't write the directrix, but I'm going to do it now. So the directrix in this case will be y equals minus p half, and here y equals p half. And here the directrix was x equals p half. Evidently, the coordinate of the focus and the number in the equation of the directrix are opposite numbers. Now, if we look at these equations, a very big question is, how do we recognize which way does the parabola go? We have actually four possibilities: opening to the right, opening to the left, opening upwards, or opening downwards. So how do we know which situation it is? So in principle, remember that S squared is always positive, and therefore the signs are determined by X. Because Y squared is always positive, but the single variable here, which is the first power, actually can determine the sign. And therefore, we can memorize this, let's say, by a trick. We look at which of the variables, is it X or is it Y, that has no square, without a square, and that variable actually tells us how the parabola opens. So if we have positive number times x, it opens in the positive x direction. If I have a negative number times x, it opens in the negative x direction. If I have positive number times y, it opens in the positive y direction. If it has a negative number times y, it opens in the negative y direction. So this is how you might remember this. And in this case, the vertex, however, in our case, the vertex is always at the origin at the 0 point. That's always. We will finish discussing equations of parabola later on. Right now, okay, all conic sections. I had some. Okay, let's see. Oh no, I will simply share another screen, which is I think it's this one. Yes, I need this. So here we have this applet. Here we have this applet where we can actually see how these conic sections are situated. So if we imagine that this okay, I will go up. Let's see. Work a little bit better. All right, there we go. So if I actually change the angle of inclination, for instance, if I have the angle 0 with respect of the base of the cone, notice that I have actually two cones, and they are supposed to be two cones, two conjugate cones, connected at the vertex. And they are infinitely long. They go infinitely far. They don't have actual base. They continue infinitely up and down. And we see how if the inclination of this intersection plane is 0, as we see 0 degrees, 0 radians, I see that the section is always a circle. The section is always a circle. You can see how it actually is depicted. Now, if I start inclining this plane, we see that the intersection actually becomes an ellipse. It might be a smaller ellipse or a greater ellipse, but it's an ellipse. And we can say that the eccentricity of this ellipse, how flat or how fat or how thin this ellipse is, it depends on the inclination, as you see. Yes.
But why didn't ellipse have two ellipses? Because it's also kind of cuts the other cone, right?
No, the thing is that you see this inclination is not steep enough. If it is steep enough, then we get this other part. But the very big problem is the interesting to see, if you see from the side, it does not intersect the other cone. See, it goes away. It goes away from it.
Yeah.
It goes away from it. That's why there's only one ellipse. However, if the steepness inclines more and becomes basically parallel, again I need to have a look. I need to, okay, like this. At the moment, see, when the ellipse becomes parallel, 45 degrees, for example, the ellipse becomes parallel to the side. This is called the generatrix of the cone, the line that you can imagine. The line is rotating about the center and generates the surface. So see, if this plane becomes parallel to the generatrix like this, then actually it never closes. The line, the curve never closes. At this moment, the authors of this applet, the inclination, probably the picture, the construction is not exact enough, so it actually makes a jump from ellipse to hyperbola, sort of the name jumps. However, at this moment, we should have the name parabola, because you see, it's still, because it's parallel, it still does not intersect the upper cone, but also because it's parallel, it never gets closed in the bottom. The ellipse is closed at the bottom if the plane is actually not so steep. The ellipse gets closed here at the bottom. But at this one specific location, at this one specific angle, not necessarily 45, it's 45 in this case for this cone. At this one specific situation, this is when parabola happens, actually. They have still marked it as hyperbola, that's because of imprecision. But basically, you can imagine that it's an ellipse that springs open. The ellipse simply springs open. The first focus is still here, but the second, that becomes the focus of the parabola. But the second focus is infinitely far away. And that's how we get the parabola as an ellipse whose other focus is very far away, infinitely far away. And that would actually mean that the eccentricity is 1 because the ratio between the infinitely far center, the distance of the infinitely far center and the vertex, and the infinitely far center and the focus, the distances are basically the same, because the center can never be reached as infinitely large. So this is a very interesting aspect of all this. And then when we increase the inclination, see what happens. The plane starts intersecting the upper cone, because now it's not parallel to the generatrix anymore. So for the parabola, it is simply parallel to the generatrix, and therefore it does not get to intersect the upper cone. Therefore, there are 3 curves, circle, ellipse, parabola, that have only 1 part, and a parabola that has the 2 parts. All right. You can perhaps, you can look up this particular applet. Actually, you can find more applets, but there those who are interested actually can look at this website, Interactive Mathematics. This is interesting. It's all about playing with things. It's not theoretically hard stuff or solving exercises, but playing around with things. I can also heartily recommend learning to deal with GeoGebra, which is a free application. GeoGebra is a free application. You are absolutely welcome to play around with that. Learn to set up parameters and again playing with some graphs and some curves if you like, or some geometrical figures. And this is where I finish. I have done 7 minutes over time. I'm very sorry for those whose patience I have tried, but I seriously hope that this will give you some impulse to investigate by yourselves, especially those who are into engineering, who need to understand things physically, who need to understand how things work physically together. All right. Thank you for your patience. I will see you on Wednesday, and have a good rest of the day.
Thank you, ma'am.
Thank you, Professor.
Goodbye.
Madam. Hello, madam. Madam, can you hear me? Madam. Madam.
Yes, what?
Madam, can you tell me what the date of changing, because I am not in Latvia.
Sorry, can you speak up? Your microphone is rather quiet.
Madam, I'm not in Latvia. So can I know the date of changing the time?
Saturday, Sunday. This weekend.
Okay.
This week.
Okay, madam.
This weekend.
Okay.
This weekend.
Okay, madam. Thank you.